Section 5.3, Day 2, Conditional Probabilities and Independence. Yesterday we actually talked about the definition of independent events. We'll review that again today. Really today what we're going to do is apply the general multiplication rule to solve probability questions. Independence. Again, when two events A and B are independent, we can simplify the general multiplication rule since the probability of B given A will equal the probability of B. Remember, independence means two events A and B are independent if the occurrences of one event have no effect on the chance that the other event will happen. If you remember our general multiplication rule, it stated the probability of A and B is equal to the probability of A times the probability of B given A, and we used a tree diagram to do the calculation. But again, since A and B are independent, B has no influence on A or vice versa, so the probability of B given A is just the probability of B. So here is the new formula for the multiplication rule if we know the events are independent, which says the probability of A and B would equal the probability of A times the probability of B. Here's an example. Following the Space Shuttle Challenger disaster, it was determined that the failure of O-ring joints in the Space Shuttle's booster rocket was to blame. Under cold conditions, it was estimated that the probability that an individual O-ring joint would function properly was 0.977. Assuming O-ring joints succeed or fail independently, what is the probability that all six would function properly? What I'm looking for is the probability that joint 1 is okay, and joint 2 is okay, and joint 3 is okay, and so forth. So all I would need to do is multiply the probability of 0.977 times itself 6 times, since I'm assuming that all the joints are independent of one another. And multiplying 0.977 times itself 6 times, I end up with 0.87. So there's an 87% chance that all 6 would function properly, leaving a 13% chance that at least one of them would fail. If we rearrange the terms in the general multiplication rule, we can get a formula for the conditional probability for the probability of B given A. Again, here's our general multiplication rule, which is the probability of A and B will equal the probability of A times the probability of B given A. To find the conditional probability, the probability of B given A, use this following formula. Again, what I'm going to do is use the general multiplication rule and solve for the probability of B given A by dividing both sides of that top equation by the probability of A. The probability of B given A is equal to the probability of A and B divided by the probability of A. Here's an example. In section 5.2 there was a problem that noted residents of a large apartment complex can be classified based on two events. A, they read the USA Today, and B, they read the New York Times. The Venn diagram below describes these residents. What I want to do with this Venn diagram is determine what is the probability that a randomly selected resident who reads the USA Today also reads the New York Times. This is a conditional probability. Based on the condition that the resident reads the USA Today, in which case there are 40% of those, I want to determine how many people also then from there read the New York Times. So here's my formula. The probability of B given A will equal the probability of A and B divided by the probability of A. So the probability of A and B is the overlap. That's who read both papers, and that's 0.05. The probability of A is the probability that someone reads the USA Today, which is 0.40, or 40%. So in taking 0.05 divided by 0.40, that's going to equal 0.125. So there is a 12.5% chance that a randomly selected resident who reads the USA Today will also be a subscriber and a reader of the New York Times. Tomorrow I'll go through the calculation of a conditional probability using a tree diagram for you. In summary, Section 5.3 in Conditional Probabilities and Independence. In this section you should have learned about conditional probabilities. If one event has happened, the chance of another event will happen is a conditional probability, and it's written as the probability of B given A. Independent events. Events A and B are independent if the chance that the event B occurs is not affected by whether A occurs or not. If two events are mutually exclusive or disjoint, they cannot be independent. When chance behavior involves a sequence of outcomes, a tree diagram can be used to describe the sample space. We had a general multiplication rule, which states that the probability of event A and B occurring together is the probability of A times the probability of B given A. In a special case, when you have two independent events, the probability of A and B occurring is just the probability of A times the probability of B. In taking the general multiplication rule, we can reorganize it to find the conditional probability formula, which states the probability of B given A is equal to the probability of A and B divided by the probability of A.